The central limit theorem, what this basically is, if you've watched my other videos, it's the same thing as the other videos. We're going to use normal distributions for the most part. And what this is, we're looking at all the possible samples of a given size instead of an individual data value or data or x value. We're looking at the distribution of all sample means for all possible samples of a given size n. And when you find the means of those means, it's actually, we're going to say it's going to be equal to the population mean. So that could be like a point estimate if you ever hear that word mentioned. However, the standard deviation is going to change. Instead of being a sigma, population standard deviation is going to change from a sigma to sigma divided by the square root of n. That's how it differs from a single data value. We're doing a sample with many data values. It also works if n is 1. We'll talk about that here in just a second, just to elaborate just a little bit. Everything is pretty much the same. The notation is a little bit different. Before we'd have z equals x minus mu over sigma. It's almost the same, except now we're doing sample means. We're doing a sample mean instead of a single sample. And the standard deviation changes. With the calculator, which is what I'm going to use, you can, if you want to see how to do it by hand, you can do the same thing I did in my previous videos and just use this formula. It's the only thing that differs. But I also use the calculator in my other videos, which may help you with this video too. But the main thing is this right here. We use this one. You can use this one for a sample size greater than 1, or actually you can use it no matter what. So whenever in doubt, use that. Because if n is 1, square root of 1 is 1, and sigma divided by 1 is sigma. So that doesn't change anything if you use that one. So what we're going to do, we're going to do some examples. If you look at the words, you'll notice some similarities. Normally distributed. We got a mean of 267. Standard deviation 15 days. 36 women, and that's our n. That's new. Before we would just have a single woman being chosen. Now it's 36 women. We're going to find the probability between 267 and 269. And the way I do this is, these are probabilities with z-scores, because all of the probabilities in this class so far use z-scores. I probably will. Not really, but for now, z-scores. So go to second vars, and we're going to use the normal CDF. This one is actually easy to do compared to the other ones, because with the calculator that is, because of where the x is between these two numbers, between 267 and 269. So 267 will be our lower, 269 will be our upper, and then our mean is 267. Yes, your mean can be one of the limits. And the standard deviation is 15. However, we have a sample size of 36. So divide that by the square root of 36, or 6. Hit enter, and we get our answer. So once again, if you're wondering what I typed in, it's this. So it's the same thing as that, except for the square root of n, or square root of n. So now let's do this one. A mean height greater than 63. The mean is 63.6. So it's going to be somewhere over here. Greater than is to the right. So x is greater than 63. Take out your calculator. Do normal vars 2. Because probability, normal is probability. Finds probability, area, so on and so on. Look at your shape. Your left bound is 63. That's your lower limit. It goes forever to the right, so use a number way bigger than 63. 1,000 always works, or not always, but tends to work. Our mean is 63.6, looks like. Standard deviation is 2.5. If it were a sample of 1, but it's not, it's a sample of 100. So divide that by the square root of 100. And we get 0.9918. The main thing about the central limit theorem is it's the sample size. It's at least 30. I didn't really mention that too much in here because with Hawks it doesn't mention a lot as far as why that's a big deal. But it's at least 30 or the population is normally distributed. 30 is a big deal. And the larger the sample size, the better the normal distribution approximation will be. So we're typically using sample sizes 30 or more. See this one? Following probability, their rebuild time is less than 8.9. The mean is what? 8.4. I look at that because I know 8.4 is in the middle, so 8.9 is going to be a little bit to the right of it. So it's going to be 8.9 and less than is going to shade it to the left. So we're looking for this. So I'll draw the picture so when I go to second vars 2, I know my left bound is a really small negative number. I'll have to use negative 1000 whenever possible. And the right bound is 8.9. And then the mean is 8.4. And the standard deviation is 1.8. Is it a single? X. So that's not single mechanic, it's 40 mechanics. So I divide that by the square root of 40. Close, close. 0.9605. Well, this one's close to it. If you get any discrepancies, probably because when this answer was found, a table was used. And this one I used the calculator. The calculator is actually more accurate. Tables round off at 4 places. Calculators probably go further. Let's look at this one. Looking for probability. And when you read these problems, there's certain things you're looking for. Probability is the main thing here. And for now, we know that's going to be a normal distribution. We know it's going to be normal because the sample size is greater than 30, greater than or equals to 30. And this one says, well, that the sample, the mean of the sample, will differ from by less than $5. So you gotta look at that. You got $75.15. That's the mean. We want to know what's probability that the mean price of the 50 pairs would differ by less than $5. Well, it doesn't say which way, either that way or this way. So you have to look at both possibilities. So $5 that way and $5 that way. So you subtract $5 from 75.15, you get 70.15, and when you add $5 to 75.15, you get 80.15. Well, that's your two bounds. So when we go to normal vars 2, we have our two bounds, 70.15, comma 80.15. And then we have our mean, which is 75.15. Then we need our standard deviation, 1789. That was a good year. I don't need a comma there. How many shoes were there? How many pairs? 50 pairs. So we divide our standard deviation by the square root of 50. Make sure you type it in correctly because I did not. It didn't feel like I did, and so I paused to make sure, and I'm glad I paused. It's 17.89. So 70.15, 80.15, 75.15 is the mean. 17.89 divided by the square root of 50 is what we use for the standard deviation, and we get 0.9 5. I use that because of sense, or probability, not sense. You do 1.59 if you want to, or something like that. Is this multiple choice? No. So there's that one. I want to check it again just to make sure I did it correctly. As far as typing everything in the way it's supposed to be typed in. 1789 divided, yeah, that's it. The awful high probability. Now let's do this one. A batch of 50 crews. We got our mean, standard deviation, more than 30. So that's central limit theorem. Their mean length differs from the population of the mean by more than 0.0004. So we get 1.625. So 0.004 and greater than, and then 0.004 and everything less than that too. It's like absolute value if you know anything about absolute value. So when I take 1.625 and add 0.004 to it, I get 1.629, so that's one bound. And when I subtract 0.004 from it, I get 1.621. And when I look at the bell-shaped curve, I put 1.629 somewhere over here, and 1.621 somewhere over there. So that's the actual range of the data values as far as different by 0.004. But then it says by more than, so more than is that way, but also more than is that way because that's going to be more than 0.004 away from the low end. That's more than 0.004 away from the high end. So what that means is I need to find one of these. When I find one of those, I can times that answer times it by 2 to get the final, because they're symmetrical. So let's bring up the calculator. So when I find one, I've already found the other. So let's do second vars 2. I'm going to do the left bound. So it's negative 1,000, comma, 1.621, comma, and then I need the mean, which is 1.625. Yep. Comma, standard deviation is 0.010. And there's, looks like 50 screws. Yep, so I divide that by the square root of 15. So the probability of this portion is 0.0023. So what that means is, to find the probability for both of those, I'll just do total, is 0.0023 times it by 2, because that's also going to be 0.0023, which is 0.0046. And I'm going to call that one the last example for this video.